Everyone knows Euler's identity. E to the I pi, plus 1, equals 0. It's often praised for its elegance. But what makes it truly remarkable is how much mathematics it contains. Recently, I took this beautiful identity one step further. I intentionally constructed an equivalent form. An equation that compresses vast areas of mathematics into a single expression. In this equivalent form of Euler's identity, we don't just see a single equation, we see an entire universe of constants. Let's walk through the top 10 mathematical constants that appear within it. First, pi, Archimedes' constant. Approximately 3.14, representing the ratio of a circle's circumference to its diameter. It's fundamental to geometry, physics, and engineering. Used to calculate the properties of circles, spheres, and waves. But pi reaches far beyond basic geometry. Appearing everywhere from orbital mechanics and signal processing to fluid dynamics and even the structure of DNA spirals. To see just how remarkable this constant is, as mathematicians developed new algorithms and computers became increasingly powerful, the number of known decimal digits of pi grew dramatically. Next, E, Euler's number. About 2.718. Serving as the base for natural logarithms and exponential functions. Crucial for modeling continuous growth/decay, population, interest, radioactive decay, and appearing in various formulas, defined by limits. And E makes the shaded area under the curve of 1 over x from the range of 1 to E equal to 1. Then comes I, the imaginary unit. Essentially defined as the square root of -1. It's not a real number, but allows for solving equations previously impossible with real numbers, forming complex numbers, a plus bi, and enabling calculations in various fields like physics and engineering. This single symbol unlocks the entire complex number system. Together, the three constants, pi, E, and I, form the core of Euler's identity itself. Now we move to structure and proportion. Phi, the golden ratio, about 1.618. Appears in geometry, art, nature, and recursive growth patterns. When a line is divided into two parts and the longer part A, divided by the smaller part, B, is equal to the sum of A, plus, B, divided by A. Gamma, the Euler Mascheroni constant, approximately 0.577, defined as the limiting difference between the harmonic series and the natural logarithm. Appears in the fields, number theory and analysis, linking discrete sums with continuous behavior and to the gamma function, hence the name, but it's unknown if it's rational or transcendental. Next are constants born directly from geometry. The Pythagorean theorem is a fundamental rule for right triangles, stating that the square of the two shorter sides, legs, A, B, equals the square of the longest side, hypotenuse, C, written as a squared plus B squared equals C squared. It helps find a missing side by plugging in known lengths, making it crucial for geometry, distance calculations, and understanding right-angled relationships in various fields. Square root 2, the Pythagorean constant, the diagonal of a unit square. The first irrational number discovered in math history. Square root 3, the Theodorus constant. The space diagonal of the unit cube. A three-dimensional extension of the same geometric principle. Finally, we reach the most fundamental numbers of all. 0, the additive identity. The concept of nothing functions as a crucial placeholder in number systems. It's also fundamental in computing, binary, false. 1, the multiplicative identity. The unit from which all scaling begins. It's also fundamental in computing, binary, true. And culturally, it denotes unity, beginnings, or excellence. And -1, the additive inverse of 1, meaning it's the number that makes 0 when added to 1, and represents a value 1 unit below 0 on the number line, distinguishing it from positive 1, the idea of direction, symmetry, and opposition. Without which subtraction, negatives, and complex numbers could not exist. It's a foundational concept in negative numbers, used in mathematics to represent quantities less than 0. When you look at them together, something profound happens. This equivalent form of Euler's identity doesn't just connect numbers, it unifies constants from geometry, algebra, calculus, number theory, and complex analysis. That's why Euler's identity isn't just beautiful. It's complete. To make sure our equivalent form of Euler's identity can capture the entire development of the complex number system, we intentionally include two key numbers, the fraction, 1/2, and the negative number, -1. Real numbers may feel obvious today, but they weren't invented all at once. It took thousands of years to build them, step by step, idea by idea. So using the numbers that appear in our equivalent form, let's walk through that story. First came the natural numbers, and later, the discovery of 0, together forming the whole numbers. Then adding negative whole numbers gave us the full concept of the integers. Next, integers combined with fractions created the rational numbers. And once irrational numbers were finally recognized and understood, all of these together formed the real number system, one of the greatest achievements in mathematical history. Finally, the discovery of imaginary numbers completed the picture, giving us the full complex number system we use today. Now that we've seen how the complex number system emerges, let's look at the operations that actually make this system work. At the most basic level, mathematics begins with binary operations. Operations that combine two numbers into one. These are the familiar arithmetic operations, addition, subtraction, multiplication, and division. They describe how numbers interact with each other. How quantities combine, separate, scale, or compare. Without binary operations, there is no algebra, no equations, and no structure. But binary operations alone are not enough. To fully describe growth, transformation, and symmetry, we need a different kind of operation, unary operations. Unary operations act on a single input. One important class is unary power operations, such as squaring a number, or applying the exponential function. When we write x squared, or e to x, we are not combining two numbers. We are transforming one number into another. These operations introduce nonlinear behavior, and they play a central role in modern mathematics and physics. Every powerful operation has an inverse. So alongside unary power operations, we also have unary inverse power operations. The square root reverses squaring. The natural logarithm reverses exponentiation. When we apply the squared root of x or ln, x, we are undoing a transformation and recovering its source. This brings us to one of the most important ideas in mathematics, identity. An identity tells us what happens when an operation has no net effect. For unary power operations, the identities are beautifully simple. The natural logarithm of 1 is 0. And the exponential of 0 is 1. ln1 is equal to 0. e to 0 is equal to 1. These identities are not coincidences. They define the fixed points of the exponential and logarithmic functions. And this is where everything connects. In the equivalent form of Euler's identity, binary operations, unary operations, inverse operations, and identities all appear at once, woven into a single, perfectly balanced equation. What makes this equivalent form so extraordinary is not just the numbers it contains, but the operations it unifies. Addition and multiplication. Exponentials and logarithms. Real numbers and imaginary numbers. All meeting in one expression. Revealing the deep structure of the complex number system itself. Let's now connect this equivalent form of Euler's identity to geometry. Because long before these numbers appeared in equations, they first appeared as lengths. The Pythagorean theorem. Everything here begins with the Pythagorean theorem. In a right triangle, the sum of the squares of the two legs is equal to the square of the hypotenuse. This single relationship, simple, visual, and exact, is the gateway from whole numbers to irrational numbers. And it appears everywhere in this diagram. The origin of the squared root of 2, geometry. Start with the unit square. Each side has length 1. Now draw the diagonal. By the Pythagorean theorem, the length of that diagonal satisfies 1 squared plus 1 squared equals 2, so the diagonal has length, squared root of 2. This is not an abstract invention. It is a geometric necessity. The moment you draw a diagonal across a square, the squared root of 2 is forced into existence. This was one of the earliest moments in history, when mathematicians realized that not all lengths can be expressed as fractions. Squared root of 2 is the first irrational number, born directly from geometry. The origin of square root 3, geometry and algebra. Now let's move up one dimension. Take a unit cube, with all edges equal to 1. First, the diagonal across a face gives us squared root of 2 again. But now we extend that diagonal through the cube, using the Pythagorean theorem a second time. 2 squared plus 1 squared equals 3. So the space diagonal has length, squared root of 3. Here, geometry and algebra work together. Geometry shows us where the squared root of 3 comes from. Algebra confirms why it must exist. This is no longer just a flat construction. It's a three-dimensional extension of the same principle. From square root 2 and square root 3 to square root 5, structure, not coincidence. Finally, look at the right triangle on the right. Its legs have length square root 2 and square root 3. Once again, the Pythagorean theorem applies. The square of the squared root of 2 plus the square of the squared root of 3 equals 2 plus 3 is equal to 5. So the hypotenuse has length, squared root of 5. This is not accidental. What you're seeing is a chain of necessity. Integers create squares. Squares create square roots. Square roots combine to create new ones. This same structure appears in the equivalent form of Euler's identity. Why this matters for the equivalent form of Euler's identity? This equivalent form is not just about special numbers. It encodes geometry through square roots, algebra through powers and sums, and structure through identities. The same relationships that govern squares, cubes, and triangles also govern exponentials, imaginary numbers, and rotations. What looks like pure algebra is quietly carrying centuries of geometric intuition. And that is why this equivalent form of Euler's identity feels so impossibly complete. It isn't just a formula. It's geometry, algebra, and number theory speaking the same language. The first three primes inside Euler's identity. Let's shift gears, from geometry to number theory. Here's the list of numbers from 1 to 100. And the first primes immediately stand out, 2, 3, and 5. Primes are the building blocks of the integers. Every whole number factors into primes, and everything starts here. Now here's the key observation. In our equivalent form of Euler's identity, the first three primes appear naturally. 2 appears through born from the diagonal of the unit square. 3 appears through from the space diagonal of the unit cube. And when those two structures combine, the square of the squared root of 2 plus the square of squared root of 3 equals 2 plus 3 equals 5. The third prime emerges. This is not coincidence. Geometry gives us square roots. Algebra squares them. And number theory reveals the primes underneath. So this equivalent form of Euler's identity doesn't just connect constants and operations. It quietly encodes the first three prime numbers, the foundation of arithmetic itself. That's why Euler's identity isn't just beautiful. It's fundamental. Alright, it's time to wrap up. Do you accept this equivalent form of Euler's identity? Let me know what you think in the comments below. And if you enjoyed this journey, don't forget to like, share, and subscribe for more beautiful mathematics. See you next time. And thanks for watching.